In this session, let us explore inverted page tables. This is an alternative approach to the traditional page table structure in operating systems. This method is designed to efficiently manage memory in systems with large virtual address spaces. We will discuss how inverted page tables work, their advantages, disadvantages, and real-world implementations. Let's compare traditional page tables with inverted page tables. Traditional page tables have one entry for each page in the virtual address space. A problem arises as modern systems have vast virtual address spaces, often 64-bit. As a result, extremely large page tables waste memory. The solution is to use inverted page tables. They use one entry per frame of physical memory, leading to more efficient memory use. The structure of inverted page tables is as follows. There is one entry per physical frame in the system. Each entry contains the process identification and the page number that occupies that frame. The size is proportional to the physical memory size and not the virtual address space. This significantly reduces memory overhead for page tables. Inverted page tables are used in systems with large virtual address spaces, such as 64-bit architectures. Let's examine address translation with inverted page tables. First, the central processing unit generates a virtual address consisting of the process identification, page number, and offset. The inverted page table is then searched for a matching process identification and page number pair. If a match is found, the index I of the entry is the physical frame number. The physical address is calculated as I multiplied by the page size, plus the offset. If no match is found, a page fault occurs. Keep in mind that the search is linear by default, which can be inefficient. Let us understand the challenges with inverted page tables. A major challenge is the linear search problem. Searching through the entire table for each address translation is inefficient. This results in a time complexity of order n lookup time, where n is the number of physical frames. This can significantly slow down memory access, especially in systems with large physical memory. Another challenge is that it is difficult to represent shared pages between processes. A solution is to use hash tables. A hash function can be used to map virtual addresses to inverted page table entries. This reduces the search time from order n to order 1 in the average case. Let's explore hashed inverted page tables. A hash function computes a hash value from the process identification and page number. The hash value is then used as an index into the hash table. The hash table entry points to the first entry in the inverted page table to check. If there is a collision, meaning multiple virtual pages hashed to the same value, follow the next pointer chain. When a match is found, the index becomes the frame number for the physical address. The next field creates a linked list of entries that hash to the same value, efficiently handling collisions. Let's explore real-world implementations of inverted page tables. The PowerPC architecture uses hash page tables, also known as HPTs, with a 64-bit address space. It implements a segment look-aside buffer, or SLB, and effective to real address translation, or ERAT caches. The IBM AIX operating system uses inverted page tables with sophisticated hashing. It is optimized for large memory systems and server workloads. Certain 64-bit mobile architectures use hybrid approaches with inverted page tables for specific memory regions, which are optimized for power efficiency and limited physical memory. To summarize, let's compare traditional page tables and inverted page tables. The size of traditional page tables is proportional to the virtual address space, while the size of inverted page tables is proportional to the physical memory size. Memory usage is high for traditional page tables, especially for 64-bit systems, but low for inverted page tables due to a fixed overhead. Lookup time is order 1 with a translation look-aside buffer, or TLB, for traditional page tables, but order n or order 1 with hashing for inverted page tables. Shared pages are easy to implement with traditional page tables, but difficult and requiring special handling with inverted page tables. Traditional page tables are simpler to implement, whereas inverted page tables are more complex, especially with hashing. Traditional page tables are best suited for systems with limited virtual address spaces, while inverted page tables are best suited for systems with large virtual address spaces. Inverted page tables are ideal for 64-bit architectures where traditional page tables would consume excessive memory. They provide significant memory savings at the cost of more complex address translation. When combined with efficient hashing techniques and hardware support, they offer a practical solution for modern systems with vast virtual address spaces and limited physical memory. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.